Hello, and welcome to the Digital Spiffy YouTube channel. This video is the first in a series covering the material on the CCNP ENCOR exam. I will be using GNS3 with Cisco CML licensing to lab the material. The lab material is sourced from the CCNP ENCOR Lab Manual version 8. I highly recommend reading the CCNP Enterprise Core 350-401 official Cert guide in conjunction with this lab material. This will provide a better understanding of the labs and what is occurring on the equipment. You can find links to these books in the description below. This video will be covering Inter-VLAN routing and reinforcing concepts related to how a network device forwards traffic from either a Layer 2 or Layer 3 perspective. Network switches add stability to a network through the creation of virtual channels. A switch maintains a table that associates a host MAC address to the port that sources the network traffic. A MAC address is a 48-bit address that is split across 6 octets and notated in hexadecimal. The first 3 octets are assigned to a device manufacturer known as the OUI, and the manufacturer ensures that the last 3 octets are unique. Here are some screenshots of a MAC address table on a switch. A tool made by Wireshark displays the manufacturer. MAC addresses operate on Layer 2 of the OSI model, which can be seen in the bottom left. This layer is known as the data link layer. An easy way to remember the OSI model is the mnemonic of all people seem to need data processing. A switch builds the MAC address table by examining the source MAC address for traffic that it receives. When a packet contains a destination MAC address that is not in the switch's MAC address table, the switch forwards the packet out of every switch port. This is known as unknown unicast flooding. All devices on the same Layer 2 segment are in the same broadcast domain and receive this packet. This screenshot of a packet capture shows the Linux machine broadcasting and searching for the MAC address of the next hop of 10.3.75.1. This is the IP address of the sub-interface for VLAN 75 on R3 in our GNS3 lab. The R3 router replies to the Linux host providing the MAC address requested for the specific IP address. ARP is the Address Resolution Protocol and provides a method of mapping Layer 3 IP addresses to Layer 2 MAC addresses by storing the IP address of a host and its corresponding MAC address. An IP host will send an ARP request via broadcast address and wait for a reply. The ARP reply includes the required Layer 2 physical MAC address of the requested host. The ARP table will hold entries for remote devices that the host has communicated with recently and devices on the same IP subnet. Virtual LANs or VLANs provide separation by creating multiple broadcast domains on the same network switch. Network devices in one VLAN cannot communicate with devices in a different VLAN via Layer 2 or broadcast traffic. VLANs are defined by the IEEE and the 802.1q standard. Each packet inside a VLAN has 32 bits added to the header. The actual VLAN ID is only 12 bits. I like to think of this as a colored flag on each packet. This colored flag represents VLAN tagging. Access ports are ports that host machines connect to. Each port has a VLAN assigned to them in the switch config. Configuring VLANs on a single switch is simply configuring each port to the VLAN number it belongs to. You can see which ports are being used for VLANs by issuing the show VLAN command on the switch. This can also be seen in the output of the show interfaces status command. Trunk ports can carry multiple VLANs and are used when VLANs need connectivity between switches or a switch and a router. When a packet is received on a trunk interface, the headers are examined and traffic is associated with the proper VLAN. 802.1q defines one special VLAN on each trunk as the native VLAN, defaulting to VLAN 1. 802.1q simply does not add an 802.1q header to frames in the native VLAN. Devices on different networks must be routed to achieve connectivity. As the data is encapsulated with its IP address, a device detects that its destination is on a different network and must be routed. The device checks its local routing table to identify its next hop IP address, which may be learned in a few different ways: a static routing entry, a default gateway, or from a routing protocol. A hop is defined as a layer 3 boundary, such as a router. The destination MAC address is needed for the next hop IP address, and this is where the ARP table is checked. Subinterfaces are virtual interfaces used on routers. This prevents each VLAN from requiring its own port on the router. A subinterface is created by adding a period and a number after the interface is specified. Then the VLAN needs to be associated with the subinterface. The relationship between R3 and D2 is considered a router on a stick model. In our lab, we will set up R3 as a router on a stick. The router on a stick model has the downside of slower performance compared to routing packets on a layer 3 switch. Multi-layer switches are a combination of a layer 2 LAN switch and a layer 3 router. A multi-layer switch can change a switch port into a routed port with the command no switch port, and then assigning an IP address for the port. In our lab, we will set up D1 as a multi-layer switch. We've covered the bases for the concepts on the network. Now it's time to open up GNS3 and configure the devices. Our first objective will be to build the network and configure basic device settings. If you were able to follow along with Packet Tracer, CML, GNS3, EVE-NG, or physical equipment, I'll be using 2 routers, 2 switches, and 4 PCs. We'll begin by dragging out all the devices we will need. I'll be using Ubuntu virtual machines and GNS3 for the PCs. Now we can label the devices in GNS3. Now we can cable the devices according to our addressing table. I'll just clean up the look here with the interface labels. With our equipment cabled, we can click the start button. These devices will take a moment to boot up, but after they do, we can console into them and begin to configure those devices. We'll start with R1, and it took a while to boot up here, but we'll just tell it that we don't want the initial config dialog, and we can terminate the auto install. So now we can enter the enable and config terminal, and we'll get the host name set up here and go ahead and do the console port so that we're not typing over our terminal output, and get the exact timeout set to 0 so we're not constantly losing console connection here. And I would only do this in the lab, not in production environment. But now we can configure some interfaces, and we'll just go by what we're seeing here in the addressing table. So the interface gig 1 connects to R3 gig 1 with the IP address 10.131, and that's a /24 on our subnet. And by default in GNS3, these ports are admin shut, so we'll just have to do a no shut after each one to bring the interface up. And this one goes to our D1 switch, and we'll just set that IP address. And now we've got our ports configured, our console configured. on R1. So now we can move on to our D1 switch, and we'll do the same kind of thing with this one that we did for R1. Do the enable, configure the host name, get into our console. And D1 will be the multi-layer switch with a routed port that goes to R1. And you'll just achieve this by getting into that interface that's connected to R1 and doing a no switch port command. And then we can assign the IP address now. And we'll just do a no shot. So in our D1 switch, we need one command that will allow it to do IP routing, and that is just the IP routing command. And we can go ahead and do our interfaces now and assign these their IP address according to our addressing table that we have over there. And just do the same thing, the no shot on these just in case. And we'll just slightly change this IP for VLAN 60. And now we can assign the ports for our PCs to the correct VLAN. So the port that PC1 connects to is the interface gig 01, and that's going to be in the VLAN 50 subnet. So we'll just do the switch port access VLAN 50. And because we have not created the VLAN, we've only interfaced it, it's going to give us that output, and that basically just means that it's now in the VLAN database. And we'll just do the same thing with the port that PC2 connects to, but with VLAN 60. Alright, D1 is configured, and now we can assign the IP addresses for our PCs. And like I said, these are Ubuntu virtual machines that I've set up in GNS3. So we'll just log into it here, and it takes a minute, so you just got to be patient with that. I'll go ahead and get PC2 going as well. And one thing that I can say is that I did connect these to the internet first to get the ifconfig stuff downloaded because they did not have the net tools installed. So if you're following along with the same type of lab environment that I am, that may be something that you want to do. But up here on the top right, we'll just connect to our Ethernet adapter, and you can see that it's trying to connect right now. The default for these is set up for DHCP, which we don't have any DHCP settings right now. So we'll just go into the IPv4 config settings, hit manual here, and if you can remember our IP addressing, this PC is 10.250.50/24 network, and the gateway is just that VLAN 50 interface. And you can click apply. And one of the things that I noticed with these is that you normally have to reboot that after applying that interface IP address. It will actually not grab it until it's rebooted, and I don't know if that's just a GNS3 thing or if that's normally how Ubuntu works, but it's always good to do the reboot after you configure that. So we'll just do the same thing here for PC2. Click the gear, go to the IPv4, go to manual. This one is the same, but in VLAN 60, so it's the 10.260.50 with a 24-bit subnet mask, and the gateway is just the IP address of the VLAN 60 interface on D1. And so we've got that set. We'll go ahead and reboot it. Alright, we've got our machines rebooted and I got logged into them, and I'm just in the terminal here, and we'll run an ifconfig to make sure our IPs are correctly assigned, and we'll open up D1 and just make sure that we're able to ping each machine from D1. That looks good, so let's see if we can ping the other machine from PC1. That one's working, and I'll just try it from PC2 to PC1 as well. Oh, that is the PC2 address, so let me fix that there. So we're able to ping the other PC from each PC, and we know that D1 has the interfaces set up correctly and the gateways are up. So we've got our PC1 and PC2 up. They can ping the default gateway and they can ping each other. But if you take a look here at the D1 routing table, it's only learning things that are directly connected to it. So what we want to do is configure a static default route for the IPv4 traffic on this D1 multi-layer switch. And a default route defines where packets will be sent if no specific route for the destination network is listed in the routing table. If no default route is set, the router will just discard all the packets with destination addresses not found in its routing table. So to do the static default route, we'll do IP route, and you can hit a question mark here, and it wants to know the destination prefix. So we'll do 0000 and the prefix mask 0000, and then you hit question mark again. It wants to know the forwarding router's address. So we'll do the gigabit 2 interface on R1. So that's 10.1.13.1. So now we have a default static route in here, and we'll just verify that is listed in the routing table. And if you take a look here, the S is static and the asterisk is default. So again, this is the static default route, sending out any traffic that is unknown or no specific route in the routing table is going out the 10.1.13.1. So it's sending that traffic to the R1 gigabit Ethernet 2 interface. So D1 has routing set up, and now we will need to configure routing on R1. This will ensure that R1 can reach devices connected to D1. And if you remember the OSI model, layer 3 uses IP addressing. R1 can't see what's connected to D1. If we look at the routing table of R1 with the show IP route command, you'll see there are no routes for the VLAN subnets assigned to D1. So we'll install a very wide route of 10.2.0.0 into R1, telling it to use the next hop of 10.1.13.13, which is D1's routed interface. So we'll just do that with the IP route, and remember this is the destination prefix. So our destination prefix, we're going to do a really wide one. We'll do that, and then this is your destination mask. So we'll just do this. And again, this is a wide route, so the next hop would be the D1 gigabit 00 interface, which is the routed interface on that multi-layer switch. So now you should be able to see those routes installed in the routing table for the 10.2 network, and you can verify that you can actually reach the 10.2 network and everything connected to that with a ping. Now we can set up the other side of our network, and we'll start with the D2 switch. This will not be a multi-layer switch like D1. We'll use a trunk port to send VLAN traffic to be routed by R3. And so first we'll do just the basic config, get the host name on here, do the line console. And we can configure our VLANs. So D2 uses VLAN 75. And do a no shut on that one. And it also does VLAN 85. And our native VLAN is going to be the 999. And we'll just no shut that one. And that'll be our native VLAN, so we'll just give it a description of native. And if you remember from earlier, we talked about the native VLAN, and 802.1q does not add a 802.1q header to frames in the native VLAN. So now that we've created our VLANs, I'll assign them for our PCs to the correct ports. And let's take a look. If you see in GNS3 at the labels, 01 is going to PC3, and PC3 is using that 75 VLAN. So switch port access VLAN 75. And we'll do this same thing with VLAN 85 on the O2 interface. And we can just verify these VLANs are assigned with the show interface status. And I'll just pipe connected to keep the output a little bit lower. And you can see this is our PC1 port, and it's got VLAN 75, and this is our PC2 port, got VLAN 85. So we can check the status of our interfaces with the show IP interface brief and pipe the up command included up so it doesn't have all the output, and you can see our interfaces for this VLAN are up. So our VLANs are all set up, and now we can do the trunk port for the VLANs to reach R3. So interface gigabit 00 connects to R3, and that'll be our trunk port. And in GNS3, we must specify the .1q encapsulation with the command switch port trunk encapsulation .1q. Then we can set the mode as trunk, so switch port mode trunk. Now we can set the native VLAN as 999 and allow the VLANs that are in use. So that command is going to be switch port trunk allowed VLAN, and then you just do each VLAN that you're allowing on here separated by commas. We can tell it our native VLAN is the 999, and you can verify that trunk interface is set up with the show interfaces trunk command, and it will show you the encapsulation that you're using and your native VLAN. So D2 is all set up. We've got the trunk interface, and we've got the ports for our PCs. So let's get over to router 3, and we'll terminate the initial config. So router 3, we'll just do the initial config, host name, line console, get our exec timeout gone. And router 3 is directly connected to router 1 with its gigabit Ethernet 1 interface, and we'll just assign that the correct IP address. Do a no shut on there, and our gigabit 2 interface will be our trunk, but we're going to do these sub interfaces. So just on the interface gigabit Ethernet 2, do a no shut, and then we'll get into the sub interfaces here. And if you remember back, we talked about sub interfaces. This will be our router on a stick. And just like the trunk on the D2, we must specify on the port the type of encapsulation to use, followed by the VLAN number that is associated with our port. So we'll just do that with the same command, encapsulation.1q. But this time we'll specify the actual VLAN. And we'll do the same thing with our VLAN 85 subinterface with the .1q85 and the correct IP address for that. And I'm just going to make sure that I actually got, I forgot to assign the subinterface for VLAN 75 the IP address, so I'll just fix that real quick. And we'll do a no shut on that as well. So now on R3 we can set up our static default route for IPv4 traffic that points to the R1 gigabit Ethernet 1 IP address. This will ensure that any traffic destined for a route not in the R3 routing table will send the traffic to R1. And we can just do a show IP route to verify the current routing table. So our static route here, IP route 0000 with these all zeros on the destination prefix mask, and the R1 gigabit Ethernet 1 IP address as a forwarding router IP address. And you could just verify that is made it to the routing table. Now we can get our PC set up for this side of the network, and I'll just log into this. Take a minute once you log in. These are Ubuntu virtual machines running in GNS3. So we'll just click the network settings, go to wired settings, click our gear here, and I've already assigned these IP addresses, so we are good to go there. Just making sure that it actually is set up here. Yep, looks good. So now we can attempt to ping PC4 from PC3. We'll just open up our terminal here. And PC4 address is in the VLAN 85. That is pinging. Now we'll just make sure the reverse is true. So our Inter-VLAN routing is working, and we would be able to ping all the PCs from the other PCs, but we did miss one step that we're going to have to go back and take care of. So if you notice, PC3 cannot reach that 10/50/50 network, which would be the PC1. And the reason for that is because R1 is missing the static default route. So you can see here in this routing table, we're going to need the static default route to get back to R3. And now that that route is in there, we can go to PC3 and we can ping the other side of the network. In the last part of the lab, we will examine CEF details on each network device. Cisco Express Forwarding is a proprietary form of scalable switching. CEF provides the ability to switch packets through a device in an efficient manner while keeping the load on the processors low. Cisco Express Forwarding is made up of two different main components, the forwarding information base and the adjacency table. The fib and the adjacency table are shortcuts that identify what interface a packet should be sent out. The command show IP CEF will display the CEF details. To view the adjacency table, the command show adjacency will show you the address of the neighbors on each interface. So if you're curious as to why that static default route fixed PC3 pinging PC1, if you remember, the static default route is for anything that's not in the routing table. So this 10.3.75.50 is not in this routing table. So before it had this static default route, it just discarded that because it wasn't in the routing table. But once we put that in there, its next hop for unknown traffic is 10.1.3.3, which is the router 3 network. Before we finish up this video, I want to do some test practice questions. Forwarding of network traffic from a layer 2 perspective uses what information? Source IP address, destination IP address, source MAC address, destination MAC address, or data protocol? D is the correct answer. The switch uses the destination MAC address to identify the port at which the packet should be forwarded. What type of network device reduces the size of a broadcast domain? Hub, switch, load balancer, or router? The correct answer is D. Broadcast domains do not cross layer 3 boundaries. Splitting a layer 2 topology into multiple subnets and joining them with a router reduces the size of the broadcast domain. CEF is composed of which components? Routing information base, forwarding information base, label information base, adjacency table, or MAC address table? The answer is B, forwarding information base, and D, adjacency table. CEF is composed of the adjacency table and the forwarding information base. Forwarding of network traffic from a layer 3 perspective uses what information? Source IP address, destination IP address, source MAC address, or destination MAC address? B. The destination IP address is used to locate the longest matching route and the outbound interface out which it should be forwarded. Which of the following statements best describe an access port on a switch? Choose 2. The access port is used to provide switch-to-switch connectivity. Frames are sent and received with 802.1q tags. The access port is used to provide host-to-switch connectivity. The switch port mode can be configured statically. C. The access port is used to provide host-to-switch connectivity, and D. The switch port mode can be configured statically. Which answer best describes the layers of the Open Systems Interconnection OSI model? 7 layers, 4 layers, 7 layers, 4 layers. A. 7 layers: application, presentation, session, transport, network, data link, physical. An easy way to remember the OSI model is a mnemonic of all people seem to need data processing. Hello, and welcome to the Digital Spiffy YouTube channel. This video is the first in a series covering the material on the CCNP ENCOR exam.